Hello there and welcome to Zero Drift, your peaceful passage through the universe. Tonight, we are going to explore one of the most beautiful and most quietly astonishing stories in the history of mathematics. A story that begins with the simplest possible question, what makes a number prime? And ends in a place of such unexpected elegance that even professional mathematicians, who have known the result for over a century, still find themselves moved by it. This is the story of the prime numbers and of the theorem that revealed the secret pattern hidden inside them. It is the story of a 15-year-old boy in the 1790s who sat alone with a notebook and counted primes by hand for hours at a time, chasing a pattern he sensed was there but could not quite see. It is the story of ancient Greeks who proved, more than 2,000 years ago, that the primes never end. It is the story of a curve that appears in the world of money and banking, of continuous interest and exponential growth, that turns out to describe, with extraordinary precision, how prime numbers thin out along the endless number line. And it is the story of a proof that took more than a century to complete, and of a conjecture made in the process that remains, to this day, the most famous unsolved problem in all of mathematics. But at its heart, it is a story about pattern and order emerging from apparent chaos. About the discovery that what looks random, when you look closely enough and patiently enough, is governed by one of the most beautiful laws in all of mathematics. About the particular kind of joy that comes from finding that the universe, even the abstract mathematical universe of numbers, is more orderly and more elegant than it had any right to be. So settle in. Let your body grow heavy and still. Let your breathing find its own slow rhythm. And allow the story of the prime numbers and the theorem that illuminated them to carry you gently towards sleep. Every number tells a story. The number 12 tells the story of 2 times 6, or 3 times 4, or 2 times 2 times 3. The number 100 tells the story of 2 times 2 times 5 times 5. The number 1000 tells the story of 2 times 2 times 2 times 5 times 5 times 5. Every composite number, every number that is not prime, can be broken down step by step into a product of smaller factors, and those factors can be broken down further, and the process continues until you reach numbers that cannot be broken down any further. Those irreducible numbers, the numbers that resist all attempts at factorization, that can only be divided evenly by 1 and by themselves, are the prime numbers. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. They are the atoms of arithmetic, the fundamental building blocks from which every other number is constructed. Every composite number is a unique product of primes, a unique fingerprint of prime factors that distinguishes it from every other number. This is the fundamental theorem of arithmetic, one of the oldest and most elegant results in all of mathematics, first articulated by Euclid more than 2,000 years ago. To understand the fundamental theorem, consider the number 24. 24 can be divided by 2, giving 12. 12 can be divided by 2, giving 6. 6 can be divided by 2, giving 3. And 3 is prime, it cannot be divided any further. So 24 is equal to 2 times 2 times 2 times 3, the product of 3 2s and a 3. That is the unique prime factorization of 24, and no other number has that same factorization. The number 84 is equal to 2 times 2 times 3 times 7, a different set of prime building blocks, a different fingerprint. The remarkable thing is that this works for every whole number greater than 1. Every such number is either prime itself, a building block, an atom, or it is a composite, a molecule built from prime atoms in a unique and specific way. The entire infinite universe of whole numbers is constructed from these indivisible primes, combined in unique products. The primes are not merely interesting, they are fundamental. They are the skeleton on which all of arithmetic is built. And yet, for all their importance, the primes are maddeningly difficult to predict. You might think that the most fundamental objects in arithmetic would reveal some kind of regularity, some pattern that would allow you to anticipate where the next one will appear, but they do not. Or at least they do not reveal their pattern easily. Let your breathing slow. The story of the primes is a story that unfolds slowly, with great patience, over centuries. And it is that patience, the willingness to sit with the question, to count and measure and compare, to resist the temptation of premature conclusions, that eventually leads to the most beautiful discovery in the story. To appreciate the mystery of the primes, it helps to spend a moment actually looking at them, to follow their appearance along the number line and notice what they do and do not reveal. Among the first 10 numbers, the primes are 2, 3, 5, and 7. 4 out of 10 numbers are prime, a density of 40%. Among the first 20 numbers, there are 8 primes, including 11, 13, 17, and 19. The density has already dropped to 40% in the first 10 to closer to 35% in the first 20. Among the first 100 numbers, there are 25 primes. Among the first 1,000, there are 168. The primes are thinning out, not dramatically, not suddenly, but steadily and unmistakably. The further you go along the number line, the less frequently you encounter a prime. This makes intuitive sense. As numbers grow larger, they have more potential divisors, more ways of being composite, more opportunities to be built from smaller prime factors. A very large number has many small primes it could potentially be divisible by, and the chance that it escapes all of them, that it is itself prime, decreases as the number grows. But thinning out is not the same as vanishing. And here is the first great surprise in the story of the primes. Despite their increasing rarity, despite the fact that you have to search further and further to find each new one, the primes never stop. There is no largest prime. The sequence of primes goes on forever, without end, into the infinite reaches of the number line. This was proved by Euclid around 300 BCE in one of the most beautiful proofs in the history of mathematics. Euclid's proof is a classic example of proof by contradiction, a technique in which you assume the opposite of what you want to prove, follow the logical consequences, and show that they lead to an impossibility, thus demonstrating that your original assumption must have been wrong. Here is the argument. Suppose, for the sake of contradiction, that there are only finitely many primes. If that were true, you could in principle list all of them, every prime that exists, collected into a finite list. Now, take all the primes in your list and multiply them together. Call the result p, then add 1 to get the number n equals p plus 1. What can you say about n? Well, n is not divisible by any of the primes in your list. Dividing n by 2 gives a remainder of 1, because p was divisible by 2, and adding 1 shifts the remainder to 1. Dividing n by 3 also gives a remainder of 1, for the same reason. Dividing n by 5, by 7, by any prime in your list, always a remainder of 1. N is divisible by none of the primes in your supposed complete list, but every whole number greater than 1 is either prime or divisible by some prime. N must fall into one of these categories. If n is prime, then it is a prime not in your original list, contradicting the assumption that you had listed all of them. If n is composite, then it has prime factors, but those factors cannot be in your list, since n is not divisible by any prime in your list. So there must be primes not in your list. Either way, your list was incomplete. The assumption that there were finitely many primes leads inevitably to a contradiction. The assumption must be false. There are infinitely many primes. Euclid's proof is celebrated not just for its conclusion, but for its method, the intellectual elegance of assuming the opposite and following the logic to destruction. It is a proof so clean and so satisfying that it has been reproduced in mathematics textbooks for 2,000 years, and it remains as compelling today as when Euclid first wrote it down. Drift a little deeper now. The room is quiet, the night is deepening. And the story moves forward from ancient Greece to the late 18th century, where a young boy is about to make a discovery that will set the course of number theory for the next 100 years. Carl Friedrich Gauss was born in Brunswick, in what is now Germany, in 1777. By every account, his mathematical abilities were apparent from an early age that bordered on the uncanny. The stories about his childhood mathematical gifts are numerous, and some are probably apocryphal, but the most famous has the ring of truth. When Gauss was perhaps 9 or 10 years old, his arithmetic teacher, reportedly trying to keep the class occupied for a long time, told the students to add up all the numbers from 1 to 100. The teacher expected this to take a while. Gauss reportedly put down his slate within seconds, having immediately seen the trick: pair each number with its partner to make 101, yielding 50 pairs, giving a sum of 5,050. Whether the story is precisely accurate or somewhat embellished in the retelling, it captures something real about Gauss's relationship with numbers, his ability to see structure where others saw only computation. When Gauss arrived at the problem of prime numbers, he was approximately 15 years old. He had been given a table of logarithms, a mathematical reference work containing the logarithms of numbers up to various limits, and he used it not just as a reference, but as a dataset. He began counting primes systematically, tallying them in blocks of 1,000 numbers, recording how many primes fell in each block, and looking for patterns in the resulting data. He had no computer, no calculator, no algorithmic shortcut beyond the sieve of Eratosthenes and the square root shortcut for checking primality. He counted by hand, over hours and days and weeks, accumulating data with the patience and systematic thoroughness that would characterize his mathematical work throughout his life. He counted primes in the first 1,000 numbers, then the second 1,000, then the third. He recorded his results and looked at them carefully. What he noticed was what any careful observer would notice after a while. The number of primes in each successive block of 1,000 was declining slowly, not dramatically, but unmistakably. The first 1,000 numbers contained 168 primes. The second 1,000 contained 134. The third 1,000 contained 127. The trend was clear. Each 1,000 numbers contained fewer primes than the 1,000 before it. This was not surprising in itself. The primes were thinning out, as we noted. But Gauss was not merely observing the thinning. He was trying to quantify it, to find a mathematical law that governed the rate at which the primes became less frequent. And in doing so, he made one of the greatest intuitive leaps in the history of mathematics. He noticed that the thinning followed the reciprocal of the natural logarithm. Not exactly, not with perfect precision, but in a way that seemed to become more and more accurate as the numbers grew larger. The average density of primes near a number x, the probability, roughly speaking, that a number near x was prime, appeared to be approximately 1 divided by the natural logarithm of x, and the total number of primes up to x appeared to be approximately the integral of this density, the accumulated sum of 1 divided by the natural logarithm, from 2 up to x. This was an extraordinary conjecture. It connected two completely different domains of mathematics: the discrete, irregular world of prime numbers and the smooth, continuous world of logarithms and calculus. It said that the apparent chaos of the primes, their seemingly random and unpredictable appearance along the number line, was governed at a deep level by one of the most fundamental and elegant functions in mathematics. Before we can fully appreciate Gauss's conjecture, we need to spend a moment with the natural logarithm itself, with what it is, where it comes from, and why it appears in the story of the primes. The natural logarithm is, in one sense, a mathematical curiosity that emerged from the study of compound interest, from questions about money growing in a bank account. Imagine you invest a sum of money at an annual interest rate of 100%. If the interest is paid once a year, at the end of the year, you have doubled your money. Simple enough. But what if the interest is paid more frequently? If it is paid twice a year, 50% every 6 months, then after 6 months you have 1.5 times your starting amount, and after another 6 months you have 1.5 times that, giving you 2.25 times your starting amount. Slightly more than if the interest were paid annually. The reason is interest on interest. The return from the first 6 months has time to earn interest of its own before the year is out. If you compound quarterly, paying 25% every 3 months, you end up with slightly more still. Compounding monthly gives more. Compounding daily gives more still. At each step, the final amount grows, but by smaller and smaller increments. The gains from compounding more frequently get smaller and smaller as you compound more often. Now ask what happens in the limit, when the interest is compounded not once a year, or once a month, or once a day, but continuously, at every instant, in an unbroken flow. This is the limit of compounding as the number of periods goes to infinity. And the answer, as Euler showed in the 18th century, is a specific and remarkable number, the number E, approximately 2.71828. This number, now called Euler's number, is one of the fundamental constants of mathematics, appearing in contexts far removed from finance, in the mathematics of growth and decay, in the theory of complex numbers, in the solutions of differential equations, throughout the entire fabric of mathematical analysis. The natural logarithm of a number x, written as ln of x, is the inverse of the exponential function with base e. It answers the question, to what power must I raise e to get x, or equivalently, in the compounding interest picture, how many years does it take for a continuously compounding investment to grow from £1 to x pounds? The natural logarithm has a characteristic shape. It starts at 0 when x equals 1, climbs steeply for small values of x, and then continues to rise but more and more slowly as x increases. For large x, the logarithm grows without bound. It eventually reaches any value you name, but it does so with agonizing slowness. The natural logarithm of a million is about 13.8. The natural logarithm of a billion is about 20.7. The natural logarithm of a trillion is about 27.6. The function grows without limit, but at a decreasing rate that makes it feel as if it might stop at any moment, even though it never does. And it was precisely this shape, this slowly growing, ever-decelerating curve, that Gauss recognized in the data on prime numbers. The average gap between consecutive primes near a number x grew like the natural logarithm of x, slowly, steadily, never stopping, but growing more and more slowly as x increased. The primes were thinning out at exactly the rate that a mathematical function derived from the theory of continuous compound interest predicted they should. Let your eyelids grow heavier as the story approaches the moment of connection, the moment when two different mathematical worlds, the discrete world of primes and the continuous world of logarithms, are found to be speaking the same language. Gauss never published his observations on the prime number theorem. He was a notoriously reluctant publisher, and many of his most important results were revealed only in letters or were found in notebooks after his death. But in a famous letter written on Christmas Eve of 1849, when Gauss was 72 years old, he described his earlier work to the astronomer Johann Franz Encke. In the letter, Gauss recalled that as a boy of 15 or 16, in the years 1792 and 1793, he had begun his systematic counting of primes. He described how he had spent countless hours tabulating primes in groups of 1,000, and how he had come to notice that the frequency of primes in each group declined at a rate governed by the reciprocal of the natural logarithm. He wrote that the number of all primes below a given limit x was approximately expressed by the integral of 1 over the natural logarithm. By what we now call the logarithmic integral, denoted Li of x. Gauss also compared his formula with a rival formula proposed by the French mathematician Adrien-Marie Legendre, who had independently published a conjecture about the distribution of primes in 1798. Legendre's formula was similar to Gauss's, but used a slightly shifted denominator, dividing by the natural logarithm minus a constant of about 1.08, which happened to fit the data better for small values of x. Gauss acknowledged that Legendre's formula was more accurate over the range they had both investigated, but argued that his logarithmic integral would prove superior in the long run, because the error in Legender's formula grew faster as x increased. In the letter, Gauss mentioned that he had investigated the distribution of primes up to 3 million, an almost incomprehensible act of hand computation. He noted, with characteristic understatement, that he had frequently spent an idle quarter of an hour to count another 1,000 here and there, though he had eventually given up without quite getting through 1,000,000. The casualness of this description should not deceive. Counting primes by hand to 3 million, checking each number for primality, recording and tabulating the results required months or years of systematic effort. It is worth pausing to appreciate what Gauss had done. In the 1790s, with nothing but pencil and paper and the mathematical knowledge available to a teenager, he had glimpsed one of the deepest results in number theory, a result that would not be rigorously proved for another century. He had seen, in the data, the fingerprint of the natural logarithm. He had sensed the connection between the continuous mathematics of logarithms and the discrete mathematics of prime numbers. And he had had the mathematical taste to recognize that this connection was not a coincidence or an approximation, but a deep structural truth about the integers. The relationship that Gauss conjectured, that the number of primes up to x, denoted by the Greek letter pi of x, not to be confused with the circle constant, is asymptotically equal to x divided by the natural logarithm of x, became known as the prime number theorem. Asymptotically equal means that the ratio of pi of x to x over log x approaches 1 as x grows without limit. The two quantities are not exactly equal for any finite x, but their percentage difference shrinks to 0 as x grows larger and larger. This is a statement of great precision and great depth. It says not merely that the primes thin out, but exactly how fast they thin out. It says that among the numbers up to x, roughly 1 in every natural logarithm of x is prime. At 1,000,000, 1 in about 14 is prime. At 1,000,000,000,000, 1 in about 27 is prime. At a Google 10 to the 100th power, 1 in about 230 is prime. The logarithm grows slowly, the primes thin out slowly, but the relationship between them is exact in the asymptotic limit. The prime number theorem was conjectured by Gauss and Legender in the late 18th century, and it remained a conjecture for nearly 100 years. During those 100 years, mathematicians made partial progress toward understanding the distribution of primes, but a complete proof remained elusive. The difficulty was that the primes are defined as purely discrete objects, whole numbers with specific divisibility properties, and connecting them to the smooth, continuous world of logarithms and calculus required mathematical tools that did not yet exist. The decisive breakthrough came in 1859, when the German mathematician Bernhard Riemann published a short paper of just 8 pages, titled On the Number of Primes Less Than a Given Magnitude. The paper is often described as one of the greatest mathematical papers ever written, and the description is not an exaggeration. In those 8 pages, Riemann recast the entire problem of prime distribution in terms of a new mathematical object, the Riemann zeta function, and in doing so connected the primes to the theory of complex analysis in a way that would eventually yield a proof of the prime number theorem and would generate mathematical questions that remain unresolved to this day. The Riemann zeta function is defined for complex numbers, numbers of the form a plus I times b, where a and b are real numbers and I is the square root of -1. For complex numbers with real part greater than 1, the zeta function is defined as the sum of 1 over n to the power of s, where s is the complex number and the sum runs over all positive integers n. This might look like a strange and abstract definition, but Riemann showed that it encodes fundamental information about the distribution of prime numbers. The connection runs through what is called the Euler product formula, which expresses the zeta function as an infinite product over prime numbers, 1 for each prime p, of 1 divided by 1 minus p to the negative s. This product formula discovered by Euler before Riemann, makes it explicit that the zeta function and the primes are deeply connected. The zeta function is built from the primes, in the sense that its values can be computed from the prime factorizations of the integers. Riemann's insight was to extend the zeta function to the entire complex plane, to define its value not just for s with real part greater than 1, but for all complex numbers except s equals 1, where it has a singularity. And he conjectured a specific and remarkable property of this extended function, that all the non-trivial zeros of the zeta function, all the complex numbers s, for which the zeta function equals 0, excluding the so-called trivial zeros at negative even integers, have real part equal to 1/2. This is the Riemann hypothesis. The Riemann hypothesis implies very precise results about the distribution of primes, about how closely pi of x approximates its asymptotic formula, and in particular about how large the error in the approximation can be. If the Riemann hypothesis is true, the primes are distributed as regularly as is theoretically possible, given the overall constraint that their density is governed by the logarithm. If it is false, there are unexpected irregularities in the distribution of primes, clumps and gaps that deviate from the logarithmic prediction by more than the hypothesis allows. The Riemann hypothesis was stated in 1859. It has not been proved. It has not been disproved. It has been verified computationally for an enormous number of zeros, billions of them, all lying on the critical line with real part 1/2, exactly as the hypothesis predicts. But a finite verification, however extensive, is not a mathematical proof. And a proof has remained elusive for more than 160 years, through the efforts of the most talented mathematicians in the world. In 2000, the Clay Mathematics Institute designated the Riemann hypothesis as one of its 7 Millennium Prize problems, the greatest unsolved problems in mathematics, and offered a prize of $1 million for its solution. It remains one of the 7 problems for which the prize has not been claimed. As you rest in the quiet of this night, let the Riemann hypothesis settle in your mind as the open door at the end of this story. The question that Gauss's patient teenage counting led to, that Riemann's 8-page paper framed with breathtaking precision, and that the best mathematical minds of the past century and a half have not yet been able to answer. The prime numbers are hiding something. We can see its outline. We cannot yet see its face. The prime number theorem itself, the statement that pi of x is asymptotically x over log x, was finally proved in 1896, independently and almost simultaneously by 2 mathematicians, the French mathematician Jacques Hadamard and the Belgian mathematician Charles-Jean de la Vallée-Poussin. Their proofs used the theory of complex functions developed by Riemann and others, and were sophisticated pieces of analysis that required the full arsenal of late 19th century mathematics. The proofs confirmed what Gauss had conjectured more than a century earlier. The primes do thin out according to the logarithm. The relationship that the young Gauss had seen in his patient hand counts of primes in the 1790s was not an approximation or a coincidence, but a mathematical truth. The fundamental theorem of arithmetic, the fact that every integer has a unique prime factorization, conspires, through mechanisms that took a century of mathematics to elucidate, to produce a distribution of primes that is as smooth and regular as the natural logarithm. The proof also established the primacy of the logarithmic integral Li of x over the simpler formula x over log x as an approximation to pi of x, the logarithmic integral. The integral of 1 over the natural logarithm from 2 to x approximates the prime counting function with much smaller error than the simpler formula, and in particular, it approximates it on the correct side. For all values of x that have been computed, Li of x is slightly larger than pi of x. It overestimates the number of primes below x. Gauss had noticed this in his computations up to 3 million. But in 1914, the British mathematician John Edensor Littlewood proved something remarkable, that pi of x must eventually exceed Li of x. Somewhere on the number line, the prime counting function must cross above the logarithmic integral and exceed it. The place where this crossing first occurs, the first number for which pi of x is greater than Li of x, is called the Skews number, after the South African mathematician Stanley Skews, who first estimated its size. The original Skews number was an astronomically large quantity, and more recent work has brought it down, but it remains far beyond the reach of direct computation. No one has ever computed pi of x directly at values of x large enough to observe the crossing. We know it must happen because Littlewood proved it, but we have never seen it. This is one of the most remarkable aspects of prime number theory, the existence of mathematical truths that have been rigorously proved, but that lie so far beyond the reach of direct computation that they have never been directly observed. The Skews crossing is one example. There are others. The mathematics of primes reaches into regions of the number line so remote that the universe itself does not contain enough matter to write down the numbers involved. There is something deeply philosophical about the prime number theorem, and it deserves attention before the story closes. It is a theorem about pattern emerging from apparent chaos, about the discovery that what looks random, when examined carefully enough and over a long enough range, is governed by a precise mathematical law. The primes individually appear random. There is no obvious formula that generates them. There is no simple rule that tells you whether the next number after any given prime will be the next prime, or whether there will be a gap of 2 or 10 or 100 before the next prime appears. The gaps between primes are erratic, irregular, unpredictable in their specific values. Mathematicians have studied the gaps between primes for centuries and have found remarkable patterns. Twin primes, pairs of primes separated by only 2, like 17 and 19 or 29 and 31, are thought to be infinitely numerous, though this has not been proved. But the individual behavior of the primes defies simple prediction. Yet at the statistical level, not asking where the next prime will be, but asking how many primes lie below a given number, the picture is perfectly clean. The prime counting function, despite its jagged individual behavior, follows the natural logarithm with a precision that becomes ever more accurate as x grows. The chaos of the individual is governed by the law of the collective. The primes are random in the small and regular in the large. This is a pattern familiar from physics, from statistical mechanics, where the random jiggling of individual molecules combines to produce the smooth, predictable behavior of gases and liquids. From thermodynamics, where the individual unpredictability of quantum events combines to produce the orderly behavior of heat and temperature. From many-body physics, where the complexity of individual interactions combines to produce the simplicity of bulk behavior. In all of these cases, looking at the collective rather than the individual reveals order that was invisible when you focused on the parts. The prime number theorem is the mathematical analog of this principle. The individual primes are unpredictable. The collective behavior of the primes is governed by the simplest and most elegant of mathematical laws. What looks like chaos is, at the statistical level, the deepest kind of order. Let that thought settle gently as the night deepens and sleep draws closer. The universe, mathematical and physical alike, contains structures that appear random at one level and reveal themselves as orderly at another. The skill of the scientist and the mathematician is knowing when to zoom in and when to zoom out, when to look at the individual and when to look at the collective, when to chase the specific and when to seek the pattern. Gauss, at 15, had that skill in abundance. He counted individual primes, and from the count he glimpsed the pattern. He zoomed in, and then he zoomed out, and in the zooming out, he saw the natural logarithm hiding in the data. 1,000 years of mathematics, 100 years of rigorous proof, and the conjecture of a patient teenager turned out to be exactly right. The story of the prime number theorem is also a story about the tools of mathematical investigation, about the interplay between data and conjecture, between computation and proof, between what we can observe and what we can rigorously demonstrate. Gauss's approach to the prime number theorem was fundamentally empirical. He gathered data, enormous quantities of data, by the standards of hand computation, and he looked for patterns. He compared different formulas, measured their accuracy, tracked the growth of their errors, and used all of this to form and refine his conjecture. He was doing, in essence, experimental mathematics, using data to guide theory, in exactly the way that experimental physicists use data to guide physical theory. This empirical approach was unusual for mathematics, which has traditionally prioritized rigorous proof over empirical observation. In mathematics, a conjecture supported by 1,000,000 examples is still just a conjecture until it is proved. The prime number theorem was supported by Gauss's extensive computations and by the computations of many subsequent mathematicians, and yet it remained a conjecture without the status of a theorem until Hadamard and de la Vallée-Poussin proved it in 1896. 100 years of empirical support were not enough. Only the proof was enough. This insistence on proof, this refusal to accept empirical evidence as a substitute for rigorous demonstration, is one of the defining characteristics of mathematics and one of its great strengths. It means that mathematical knowledge, once established, is permanent and certain in a way that scientific knowledge is not. The prime number theorem, proved in 1896, is as true today as it was then. No future observation or experiment could overturn it. It is a truth about the integers that will remain true as long as mathematics exists. And yet the empirical approach was essential to finding the truth in the first place. Without Gauss's patient counting, without his comparison of formulas, without his quantitative assessment of their errors, the prime number theorem might not have been conjectured until much later, if at all. The data came first. The pattern came from the data. The conjecture came from the pattern. And the proof, which took another 100 years, confirmed what the data had always suggested. This is the scientific method applied to mathematics. Respect the data, form a conjecture, test it, and then, finally, prove it. The sieve of Eratosthenes deserves a moment of its own in this story, not because it is the most mathematically deep result we have discussed, but because it is one of the most beautiful. A simple, visual, almost physical procedure for finding prime numbers that was invented by the Greek mathematician Eratosthenes around 240 BCE, and that remains one of the most elegant algorithms in the history of mathematics. Eratosthenes was a remarkable figure in his own right, the chief librarian of the Library of Alexandria, the man who first calculated the circumference of the Earth with surprising accuracy using the geometry of shadows, a polymath of the ancient world who made lasting contributions to geography, chronology, and mathematics. His sieve is, in its way, a fitting product of such a mind, a procedure that is simultaneously simple enough for a child to follow and profound enough to yield deep mathematical insight. The sieve works as follows. Write down all the integers from 2 to whatever limit you choose. Start with 2, the first prime. Circle it, and then cross out every subsequent multiple of 2 in the list. All the multiples of 2, 4, 6, 8, 10, and so on are composite, and the sieve eliminates them at one stroke. Move to the next uncircled number, 3, the second prime. Circle it and cross out every multiple of 3. Move to the next uncircled number, 5, circle it and cross out its multiples. Continue. At each step, the next uncircled number is automatically prime. All its smaller factors have already been eliminated, so it has no factors smaller than itself, other than 1. The procedure sifts the composite numbers out of the list, leaving behind only the primes, like gold remaining in a pan after the lighter gravel has been washed away. The sieve of Eratosthenes is not the most efficient algorithm for finding large primes. For that, more sophisticated modern methods are available, but it is the most transparent and the most beautiful. Watching it work, crossing out multiples and watching the primes emerge gives an immediate visual intuition for what the primes are and how they relate to the composites. Every number that survives the sieve is prime because it is not divisible by any of the primes that came before it. It is genuinely irreducible, a new atomic building block, not a molecule assembled from smaller pieces. It was from precisely this visual and tactile understanding of the primes that Gauss built his deeper investigation. He knew the sieve. He knew how to check primality. He used these tools to count primes systematically, and from those counts, he distilled his conjecture. The sieve of Eratosthenes was the foundation. The prime number theorem was the cathedral built on that foundation centuries later. The prime number theorem has practical applications that extend far beyond pure mathematics, applications that touch the daily lives of almost everyone in the modern world, even if those people have never heard of the prime number theorem. The most important of these applications is cryptography, the science of secure communication. Modern cryptographic systems, including the systems that protect internet banking, secure email, and online commerce, rely on the difficulty of certain mathematical problems involving prime numbers. The most widely used such system, the RSA algorithm developed in the 1970s, works by taking two large prime numbers and multiplying them together. The product of two large primes is easy to compute, but extremely hard to factor back into its prime components, even with the most powerful computers available. Factoring a number that is the product of two sufficiently large primes requires more time than the age of the universe. The security of RSA cryptography rests on this asymmetry. Multiplication is easy, factoring is hard. And the prime number theorem is relevant because it tells you how many primes are available for use as cryptographic keys. If you want to choose a large prime number for use in an RSA key, you need to know that large prime numbers exist in sufficient abundance. The prime number theorem tells you that among numbers with n digits, roughly 1 in n times the natural logarithm of 10 is prime, about 1 in 3 times n for a number with 1,000 digits, roughly 1 in every 2,300 numbers is prime. There are plenty of primes available, even at cryptographically useful sizes, and the prime number theorem tells you exactly how many to expect. The digital security infrastructure that underlies modern commerce and communication, the technology that allows you to send a credit card number over the internet without fear that someone is eavesdropping, depends, at its mathematical foundations, on the distribution of prime numbers. The prime number theorem, which Gauss conjectured while counting primes by hand in the 1790s, is woven into the fabric of the digital world. The night is deep around you now, and the story of the prime number theorem has reached its resting place. We began with the most basic question about numbers: what makes a number prime? And we followed that question through 2,000 years of mathematics, from Euclid's proof of the infinitude of primes, to Gauss's patient teenage counting, to Riemann's 8-page masterpiece, to the proofs of Hadamard and de la Vallée-Poussin. We discovered that the apparent randomness of the primes conceals a deep and beautiful regularity, that the prime counting function follows the natural logarithm with a precision that becomes ever more exact as the numbers grow larger. We saw the connection between the discrete world of primes and the continuous world of logarithms and calculus, a connection that feels surprising and that turns out to be profoundly true. And we glimpsed the great open question that the prime number theorem generated along the way, the Riemann hypothesis, the conjecture that all the non-trivial zeros of the Riemann zeta function lie on the critical line with real part 1/2, unproved since 1859 and still waiting for a mathematician who can reach it. The story of the prime numbers is not finished. The prime number theorem is proved, but the Riemann hypothesis stands open. The distribution of prime gaps, the distances between consecutive primes, is understood in broad outline but not in detail. Twin primes, primes separated by 2, are thought to be infinitely numerous, but this has not been proved. Many of the most natural questions about prime numbers remain open, resistant to the cleverest techniques that the best mathematicians of our era can bring to bear. The primes are infinitely numerous, infinitely various, governed in the large by the natural logarithm and in the small by a randomness that mimics chaos while hiding deep structure. They are the atoms of arithmetic, the foundation on which the entire universe of numbers is built, and they have been revealing their secrets to patient human minds for more than 2,000 years, and they are not done yet. To understand why the prime number theorem is so surprising, it helps to appreciate just how different the world of prime numbers looks up close compared to how it looks from a distance. Up close, the primes are utterly irregular. They appear and disappear without warning, separated by gaps of wildly varying size. Between 2 and 3, the gap is 1. Between 3 and 5, the gap is 2. Between 7 and 11, the gap is 4. Between 23 and 29, the gap is 6. Between 89 and 97, the gap is 8. And for large enough numbers, the gaps can be arbitrarily large. For any number n you choose, there exist n consecutive composite numbers, because the numbers from n plus 2 factorial plus 2 up to n plus 2 factorial plus n plus 1 are all composite, each one divisible by the corresponding factor in the factorial. So the primes can stay away for arbitrarily long stretches, and yet they always come back. After any gap, however long, another prime eventually appears. The primes are simultaneously capable of very long absences and guaranteed never to disappear permanently. This combination of local wildness and global regularity is what makes them so fascinating and so mathematically rich. The local wildness shows itself in the gaps. The global regularity shows itself in the prime counting function, in the way pi of x tracks x divided by log x with ever-increasing precision. The two aspects of the primes, the wildness and the regularity, coexist, and they are both true simultaneously. Neither cancels the other. Each is real at its own scale. This is deeply reminiscent of the behavior of physical systems at different scales. At the microscopic scale, matter consists of atoms jiggling with thermal energy, electrons moving in complex orbits, quantum fluctuations introducing irreducible randomness into every measurement. At the macroscopic scale, the same matter displays smooth, deterministic behavior. A metal rod expands predictably when heated, water flows in patterns described by the equations of fluid dynamics. A planet follows its orbit with the precision that allows eclipses to be predicted centuries in advance. The microscopic wildness and the macroscopic regularity coexist, and neither is more real than the other. The prime number theorem is the mathematical analog of this physical phenomenon. It says that the wildness of the primes at the individual level does not prevent their distribution from being perfectly regular at the statistical level. The chaos of the specific is governed by the law of the collective. This is one of the deepest and most important themes in all of mathematics and physics, the emergence of order from apparent disorder when you look at the right scale. The history of attempts to find patterns in the primes before Gauss is a long and instructive story about the difficulty of the problem and about the difference between finding patterns and proving them. The ancient Greeks were fascinated by prime numbers, as they were by many aspects of number theory, and they made several important discoveries. Euclid proved the infinitude of primes. Eratosthenes invented the sieve. Euclid also developed the theory of perfect numbers, numbers that equal the sum of their proper divisors, like 6, which equals 1 plus 2 plus 3, and connected them to what are now called Mersenne primes, primes of the form 2 to the power of n minus 1. Perfect numbers and Mersenne primes are still actively studied today, and the largest known prime is always a Mersenne prime, because the special form of Mersenne numbers makes them amenable to the fastest known primality testing algorithms. In the 16th and 17th centuries, as algebra and arithmetic developed into more sophisticated tools, mathematicians tried to find formulas that would generate prime numbers. Marin Mersenne himself, a French friar and mathematician who was a central figure in the scientific correspondence networks of the early 17th century, investigated primes of the form 2 to the n-1, hoping to find a pattern in which values of n produced primes. He compiled a list that was partly correct and partly wrong, but the investigation was productive because it led to the development of better tools for testing primality. Pierre de Fermat, the great French mathematician of the 17th century, conjectured that numbers of the form 2 to the power of 2 to the n+1, the Fermat numbers, were all prime. The first 5 Fermat numbers, 3, 5, 17, 257, and 65,537, are indeed prime. Fermat believed the pattern would continue forever. In 1732, Euler demonstrated that the 6th Fermat number, 2 to the 32nd power plus 1, which equals 4,294,967,297, is composite. It equals 641 times 6,700,047. Not a single Fermat number beyond the 5th has been found to be prime, and many have been shown to be composite, though no one has proved whether there are infinitely many Fermat primes or only finitely many. These early investigations illustrate a recurring theme in the mathematics of primes: the apparent pattern that fails upon closer examination, the conjecture that turns out to be wrong or that remains unproved. The primes are extraordinarily good at suggesting false regularities, at letting you see a pattern in a small sample that does not persist to larger numbers. This is why Gauss's empirical approach, checking the pattern against data, tracking the error, pushing the comparison to larger and larger values of x, was so important. He did not trust the pattern until he had tested it extensively, and he resisted making any claims stronger than the data could support. In his Christmas Eve letter to Encke, Gauss was careful to describe his conjecture in qualified terms. He did not assert that the prime counting function was exactly equal to x over log x or to the logarithmic integral. He said it was approximately equal, and he quantified the approximation with data. He noticed that the logarithmic integral was more accurate than x over log x, and he noted that the error in the logarithmic integral approximation grew more slowly than Legender's formula suggested. He was careful, precise, and appropriately humble about what the data could and could not establish. This scientific temperament, the willingness to be guided by data, the reluctance to overstate conclusions, the insistence on quantifying rather than merely asserting, is part of what made Gauss the greatest mathematician of his era. He had the insight to see the pattern and the discipline to see its limits. The connection between the prime number theorem and the natural logarithm becomes even more beautiful when you think about it from the perspective of probability. The prime number theorem says that the density of primes near a large number x is approximately 1 divided by the natural logarithm of x. This means that if you pick a random number near x, a number chosen uniformly at random from the integers in the vicinity of x, the probability that it is prime is approximately 1 over the natural logarithm of x. This is a statement about probability in the most literal sense. The primes behave, in their large-scale distribution, as if each integer had been independently declared prime with probability 1 over its natural logarithm. This is sometimes called the Craméa random model of the primes, a heuristic model in which the primes are treated as a random subset of the integers with a probability of inclusion that decreases like the reciprocal of the logarithm. The Craméa model is not a theorem. The primes are not actually random. Any given number is either prime or it is not, and this is a definite mathematical fact, not a probabilistic one. But the model captures the large-scale statistical behavior of the primes with impressive accuracy. It correctly predicts not just the overall density of the primes, but many finer statistical properties. the distribution of gaps between primes, the frequency of prime pairs and prime triplets, and many other features of the prime distribution that would be expected if the primes were drawn from a random process with the right probability. The deep reason why the Cramea model works so well is not fully understood, and understanding it better is one of the goals of current research in analytic number theory. The Riemann hypothesis, if proved, would imply very precise results about how well the primes conform to random behavior. Essentially, it would say that the primes are as random as they can possibly be, given that their density is governed by the logarithm. The primes would be, in a precise statistical sense, maximally random within the constraint of their density. This maximally random behavior within a constraint is another deep theme that appears throughout mathematics and physics. In statistical mechanics, the equilibrium state of a physical system is the one that maximizes entropy, that is maximally disordered, subject to the constraints of fixed total energy and particle number. In information theory, the distribution that maximizes information entropy subject to given constraints is the one that is, in a sense, maximally random or maximally surprising. The Riemann hypothesis, if it is true, says that the primes are the maximally random sequence consistent with their logarithmic density, that they exploit every degree of freedom available to them within the constraint that their average density is 1 over the logarithm. This connection between prime number theory and the mathematics of randomness and entropy is one of the most beautiful and most unexpected in all of mathematics. It suggests that the prime numbers are not just fundamental building blocks of arithmetic, but also optimal, in a statistical sense, that they are arranged in the most disordered possible way consistent with their overall density. The universe of numbers is not just lawful. It is, in this specific sense, as wild and as free as the laws permit. There is a quiet heroism in the story of mathematical discovery that is easy to overlook when you focus on the results rather than the process. The prime number theorem was not discovered by a sudden flash of inspiration, though Gauss's initial insight had something of that quality. It was built up slowly, over decades, by the accumulation of computation and the gradual refinement of conjecture. And the proof, when it finally came, represented the culmination of a century of mathematical development, the creation of complex analysis, the theory of analytic functions, the study of the Riemann zeta function that was itself driven, in part, by the desire to understand the primes. Mathematics advances the way science advances, not always in a straight line, not always efficiently, but relentlessly, with each generation building on the work of the previous one, each insight opening new possibilities, each proof inspiring new questions. The prime number theorem took from Euclid's infinitude proof around 300 BCE to Gauss's conjecture around 1792 to Riemann's zeta function in 1859 to the proofs of Hadamard and de la Vallée-Poussin in 1896. A span of more than 2,000 years from the first real mathematical investigation of the primes to the proof of the prime number theorem. And in those 2,000 years, the question never went away. Mathematicians in every era returned to it, added what they could, passed it on. The question outlasted individuals, outlasted civilizations, outlasted the rise and fall of empires, and the transformation of human culture. It was posed by ancient Greeks, investigated by Renaissance scholars, quantified by an 18th century genius, reformulated by a 19th century master, and finally proved by two mathematicians working independently at the turn of the 20th century. The question was bigger than any of them, and all of them together were needed to answer it. This is mathematics at its grandest, a human conversation that spans millennia, each generation speaking to the next across the barrier of time, building something that no individual could build alone, moving toward truths that are, once established, permanent and indestructible. Gauss, in his Christmas Eve letter, described his mathematical process with characteristic modesty. He said that he had spent idle quarter hours counting primes, that he had lacked the patience for a continuous count, that he had eventually given up without quite getting through 1,000,000. But those idle quarter hours, those scattered sessions of patient counting, produced the deepest conjecture in the history of number theory. The patience was there, even if Gauss chose to understate it. The curiosity was there, driving him back to the numbers again and again. The mathematical taste was there, allowing him to recognize the natural logarithm in the pattern of the data. Gauss also wrote, near the end of his life, that it was not knowledge, but the act of learning that granted the greatest enjoyment, not possession, but the act of getting there. The prime number theorem, for Gauss, was not a possession. It was a journey that he began at 15 and that he never quite completed because the proof was beyond his reach. But the act of learning, the act of counting and comparing and conjecturing, was in itself a source of deep satisfaction. That is a kind of wisdom worth carrying with you into sleep. The value of inquiry lies in the inquiry itself, not merely in the answer. The primes invited Gauss to look, and he looked, and what he saw was beautiful. The proof came later, worked out by others, but the seeing came first, and the seeing was its own reward. Among the many remarkable features of the prime number theorem, one of the most philosophically interesting is what it says about the relationship between mathematics and the physical world. The natural logarithm arose originally in the context of compound interest, a financial calculation, a practical tool for bankers and merchants. It then appeared in the study of exponential growth and decay, in the mathematics of population dynamics and radioactive decay, in the theory of information and entropy, in the solutions of differential equations that describe physical processes of every kind. And then, mysteriously, it appears in the distribution of prime numbers, in a domain that seems as far from the practical world of finance and physics as anything could be. The prime numbers are defined by a simple mathematical property, being divisible only by 1 and themselves, and there is no obvious reason why the frequency of such numbers should have anything to do with the mathematics of continuous growth and compound interest. Yet it does. The natural logarithm, which arose from thinking about money growing in a bank, governs the distribution of the indivisible atoms of arithmetic. This is an example of what the physicist and mathematician Eugene Wigner called the unreasonable effectiveness of mathematics, the mysterious fact that mathematical structures developed for one purpose, or for no practical purpose at all, turn out to describe phenomena in completely unrelated domains. The natural logarithm was not invented to describe prime numbers. It arose from a specific context and then was found to apply, with exact asymptotic precision, to a completely different mathematical phenomenon. This is not a coincidence, but a sign of the deep connections that run through mathematics, the way mathematical truths, once established, apply far beyond the domain in which they were discovered. The same phenomenon appears throughout mathematics and physics. The mathematics of curved surfaces, developed by Gauss himself in the early 19th century, turned out to be the mathematical language of Einstein's general theory of relativity 100 years later, a language that described the curvature of spacetime, a concept that Gauss could not have anticipated. The theory of complex numbers, developed as a purely abstract mathematical tool for solving polynomial equations, turned out to be the fundamental language of quantum mechanics, the theory of physical reality at the atomic scale. The theory of symmetry, developed by Galois and others in the 19th century to study polynomial equations, turned out to be the organizing principle of particle physics in the 20th century. Mathematics keeps turning out to be the right language for describing physical reality, and this continues to work in domains, like prime number theory, that seem entirely divorced from any physical application. The prime number theorem describes a property of the integers, which are among the most abstract objects in mathematics. And yet the natural logarithm that governs prime distribution is the same function that governs compound interest, radioactive decay, the loudness of sound, the brightness of stars. The mathematical universe and the physical universe are connected by threads that we are only beginning to trace. The question of why mathematics is so effective at describing reality is one of the deepest questions in the philosophy of science, and it does not have a universally agreed answer. Some philosophers and mathematicians believe that mathematics is discovered rather than invented, that mathematical truths exist independently of human minds in some abstract realm of forms, and that mathematicians are explorers who map that realm rather than builders who construct it. On this view, the effectiveness of mathematics in describing physical reality is not surprising, because both mathematics and physics are describing the same underlying reality, the mathematical structure of the universe. Others believe that mathematics is a human invention, a language developed by human minds to describe patterns in the world, shaped by the structure of our cognitive faculties and by the practical needs that drove the development of mathematical concepts. On this view, the effectiveness of mathematics is less surprising because mathematics was always, at some level, developed in response to the need to describe the world. The prime number theorem does not resolve this philosophical debate, but it adds an interesting data point. The natural logarithm was not developed to describe prime numbers. It emerged from the study of areas under curves and from the theory of compound interest, and it was recognized as a fundamental function for independent reasons. The fact that it also governs prime distribution was discovered empirically through the kind of patient counting and comparison that Gauss did, not by philosophical argument. It was a surprise. If mathematics is a human invention, it is a remarkably surprising one that keeps turning out to describe things that were not in view when the mathematical tools were being developed. If mathematics is a discovery, then the prime number theorem is one of the most beautiful examples of the mathematical structure of reality revealing itself through careful human inquiry. Either way, the prime number theorem is a reminder that the most abstract and apparently useless mathematics has a way of turning out to be deeply connected to the rest of knowledge. Gauss's teenage counting project, which must have seemed to an outside observer like a peculiar way to spend one's spare time, produced a result that is now woven into the foundations of modern cryptography, into the theory of the Riemann zeta function, into some of the deepest open questions in mathematics. The investment of patient attention paid dividends that compound mathematically for centuries. As the final quiet descends, there is one more aspect of the prime number theorem worth carrying into sleep: the aesthetic dimension, the quality of beauty that mathematicians consistently use to describe results like this one. Mathematical beauty is difficult to define but easy to recognize. It has to do with surprise, with the discovery that things that appeared unrelated are deeply connected. It has to do with economy, with results that say a great deal in a small space, like the statement that pi of x is asymptotically x over log x. It has to do with depth, with results that open up new questions and new connections rather than closing off investigation. And it has to do with the feeling that something inevitable has been revealed, that once you see the result, you cannot imagine the mathematics being any other way. The prime number theorem has all of these qualities: the surprise of finding the natural logarithm in the primes, the economy of the asymptotic statement, the depth that opened into the Riemann hypothesis, and a century of subsequent research. And the sense of inevitability, the feeling, once you understand the argument, that of course the primes thin out according to the logarithm, that there could hardly be any other law governing their distribution. This combination of surprise and inevitability is the hallmark of deep mathematical truth. It feels surprising because we did not see it coming. It feels inevitable because once we see it, we cannot unsee it, and the mathematics would feel incomplete and wrong if the result were false. The prime number theorem is one of those results that once you know it, you cannot imagine not knowing it. The primes are there, along the number line, in their infinite, irregular, never-repeating sequence. And the natural logarithm is there, bending gently and inevitably upward, governing their distribution with quiet precision. The two things are connected, and the connection is beautiful, and a 15-year-old boy with a notebook saw it first. That is a story worth carrying into sleep, and it will still be true when you wake. There is something particularly moving about the story of Carl Friedrich Gauss counting primes alone in the 1790s, because it speaks to something universal about the mathematical impulse, the desire to find order, to find pattern, to find the law underneath the apparent chaos. This desire is not unique to professional mathematicians. It is one of the most basic human cognitive drives, present in children who notice patterns in tiles and leaves and clouds, in scientists who notice regularities in data and pursue them to their theoretical conclusions, in artists and musicians who find and create structure in the raw material of sound and image and language. Gauss happened to direct this impulse toward prime numbers, and he happened to have the mathematical tools to act on what he found. But the impulse itself is something everyone has felt, the sense that the chaos is not quite as chaotic as it looks, that there is something underneath it, that patience and attention will eventually reveal the pattern. The prime number theorem is the vindication of that sense, applied to one of the most apparently chaotic domains imaginable. The primes, which look from close up like a random scattering, reveal from far away the most elegant and fundamental of mathematical curves. The universe of numbers, which is vast and complex and full of surprises, is also governed by laws as clean and as beautiful as the laws of physics. This is what mathematics at its best does. It takes the overwhelming complexity of a mathematical landscape and finds, underneath it, a simple and beautiful truth. The truth was always there. It did not become true when Gauss conjectured it or when Hadamard proved it. It was true when the first prime number existed, which was before the universe was old enough to contain minds that could notice. The mathematicians did not create the prime number theorem. They discovered it. And the discovery, when it came, was the product of patience and curiosity and a willingness to sit with a hard question for a very long time, 2,000 years, from Euclid to the proof of 1896. Some of the people who contributed to that discovery knew they were contributing to something larger than themselves. Others, like the teenage Gauss, were simply following their curiosity wherever it led. But the cumulative effect of all that individual curiosity, all that patient counting and comparison and conjecturing and proving, was a result of breathtaking beauty and depth. The largest known prime number, as of recent years, has more than 24 million decimal digits. It was discovered in 2018 by Patrick Laroche, a volunteer in the Great Internet Mersenne Prime Search, a distributed computing project in which volunteers around the world donate the unused processing power of their computers to searching for large Mersenne primes. The prime Laroche found is a Mersenne prime of the form 2 to the power of n-1, with n equal to 82,589,933. If you were to print this number in standard 12-point type, it would fill roughly 7,000 pages. It is a number so large that it cannot be held in a human mind in any direct sense. You can only relate to it through its properties, through the knowledge that it is prime, that it is larger than any prime previously known, that it has a specific number of digits. The number itself is beyond direct comprehension, and yet it is prime. It has no factors other than 1 and itself. You cannot divide it evenly by 2, or by 3, or by any prime up to its square root. It is, in the most fundamental sense, an atom, irreducible, indivisible, a pure building block of arithmetic. And the prime number theorem tells us approximately how many primes of this size to expect. The density of primes near a number with 24 million digits is roughly 1 over 55 million. Relatively rare, but present, and findable with sufficient computational effort. The search for large primes is partly a test of computing power and mathematical algorithms, and partly an act of mathematical exploration, an extension of the project that Gauss began with his notebook, pushing the investigation of primes into larger and larger territory. Each new record prime found extends the empirical verification of the prime number theorem to another region of the number line. And somewhere beyond the largest known prime, infinitely many more primes wait, undiscovered, their precise locations unknown, their existence guaranteed by Euclid's 2,000-year-old proof. The number line extends without limit, the primes thin out without disappearing, and the natural logarithm governs their distribution with quiet, relentless precision. Before the story closes, there is one final beautiful fact about prime numbers that deserves to be mentioned, not because it connects directly to the prime number theorem, but because it captures something of the inexhaustible richness of the primes that makes them so compelling to mathematicians. It is the fact about twin primes, pairs of prime numbers that differ by exactly 2. 3 and 5 are twin primes. 11 and 13 are twin primes. 17 and 19 are twin primes. 29 and 31 are twin primes. As the numbers grow larger, twin primes become rarer, just as individual primes become rarer. But do they ever stop? The twin prime conjecture, the conjecture that there are infinitely many twin primes, has been open since the 19th century. It is one of the simplest statements about prime numbers you can make, and it has resisted proof for more than 150 years. Until 2013, mathematicians had not even come close to proving it. Then, in May of 2013, a virtually unknown mathematician named Yitang Zhang, who had been working in relative obscurity, published a paper proving that there are infinitely many pairs of primes separated by at most 70 million. This was a breakthrough of the first order, not the twin prime conjecture itself, but the first finite bound on prime gaps, the first proof that prime pairs with a bounded gap occur infinitely often. Within months, the Polymath Project, a collaborative mathematical research initiative, had reduced the bound from 70 million to 600, and then further still. The current best bound, achieved by James Maynard in 2013 independently of Zhang, is that there are infinitely many prime pairs with a gap of at most 600. The twin prime conjecture itself, the claim that the bound can be reduced all the way to 2, remains open. But the progress in 2013 showed that it is approachable, that the tools being developed in analytic number theory are powerful enough to make real inroads into questions that had seemed completely resistant. The story of the prime number theorem is not the end of the story of the primes. It is one chapter in a continuing investigation that shows no sign of running out of material. The primes are endlessly fascinating, endlessly productive, endlessly surprising. They have occupied mathematicians for 2,000 years, and they will occupy them for 2,000 more. Each answer generates new questions. Each proof opens new territory. The investigation is self-renewing because the subject matter is inexhaustible. That inexhaustibility is itself a kind of comfort. The primes will always be there, along the infinite number line, waiting to be counted and measured and conjectured about and proved. The curiosity that drove Gauss to spend his idle quarter hours counting by hand will drive future mathematicians to their own patient investigations, using tools that do not yet exist to answer questions that have not yet been asked. And when they find what they are looking for, it will have been there all along, true before anyone knew it, waiting for a mind patient enough to see it. Let the primes rest now, quiet along the number line, each one a tiny, irreducible fact in the infinite arithmetic of the universe. They will be there in the morning, just as they are now, just as they have always been, true and beautiful and inexhaustible. The story of mathematics is not finished. It never is. And that is the most beautiful thing about it. The mathematician G.H. Hardy, who spent much of his career working in analytic number theory and who collaborated with the Indian mathematical genius Srinivasa Ramanujan in one of the most remarkable partnerships in the history of mathematics, wrote in his memoir, A Mathematician's Apology, that a mathematician, like a painter or a poet, is a maker of patterns. If his patterns are more permanent than theirs, it is because they are made with ideas. The prime number theorem is one of the most permanent patterns ever made. The pattern it describes, the relationship between the distribution of primes and the natural logarithm, is not a pattern imposed on reality by human minds. It is a pattern that is inherent in the structure of the integers, present whether or not any mind has noticed it, true in every universe in which the natural numbers exist. The prime number theorem would be true if no human being had ever lived. It was true before the Earth formed. It will be true after the sun has burned out. This permanence is what Hardy meant when he said that mathematical patterns are more permanent than the patterns of poets and painters. A poem can be lost. A painting can decay. A mathematical truth, once proved, cannot be unproved. It cannot become false. It is as permanent as anything in the universe can be. And the prime number theorem is a particularly beautiful example of this permanence, because it required 2,000 years of mathematical effort to establish, and that effort did not change the theorem, it revealed it. Euclid did not create the infinitude of primes by proving it. He discovered that the primes are infinite, a fact that was already true. Gauss did not create the logarithmic distribution of primes by conjecturing it. He noticed a pattern that was already there, in the numbers, waiting to be seen. Riemann did not create the connection between the zeta function and the primes by identifying it. He found a pre-existing structure in the mathematics of complex functions that had always been connected to the primes. The theorem was always true. The mathematicians simply learned to see it. This is one of the most comforting ideas in all of mathematics, that truth is there, waiting, independent of whether any mind has found it. The pattern of the primes was not uncertain before Gauss noticed it. The natural logarithm was not lurking in the distribution of primes only from 1792 onward. The connection was always there, inherent in the structure of arithmetic, as inevitable as 2 + 2 = 4. We live in a universe that contains, among other things, the integers 1, 2, 3, and so on, without end. And among the integers, the primes are scattered according to the natural logarithm, thinning out as the numbers grow but never disappearing, forming a distribution that is as precise and as beautiful as any physical law. This was true before there were minds to know it, and it will be true after the last mind in the universe has thought its last thought. That permanence, that inexorable, impersonal mathematical truth, is the final gift of the prime number theorem. Not just the theorem itself, not just the beautiful connection between primes and logarithms, but the demonstration that such permanent truths exist, that the universe is not merely physical, not merely quarks and fields and curved spacetime, but also mathematical. That the integers and their properties are as real as the atoms of your body and more permanent. You are lying in the dark, warm and still, and somewhere far below the level of atoms and nuclei and quarks, the integers run on forever, and the primes are scattered among them according to the natural logarithm, and this has been true forever and will be true forever. And tonight, for a few moments, you knew it. That is more than enough. Rest now. The connection between the prime number theorem and the Riemann hypothesis deserves one more moment of attention, because it illustrates something profound about the relationship between what we know and what we are trying to know, between the proved and the conjectured, between the established and the open. The prime number theorem tells us the average behavior of the primes, how many of them lie below a given number to leading order, but averages hide fluctuations. The prime counting function pi of x is not exactly equal to the logarithmic integral li of x. It oscillates around it, sometimes above and sometimes below, deviating by varying amounts at different values of x. The prime number theorem says that these deviations, as a fraction of the total count, shrink to zero as x grows, but it says nothing about how large the deviations can be in absolute terms. The Riemann hypothesis controls the deviations. If the Riemann hypothesis is true, then the error in the prime number theorem, the difference between pi of x and its logarithmic integral approximation, is bounded by approximately the square root of x times the natural logarithm of x if the Riemann hypothesis is false. If some of the non-trivial zeros of the zeta function lie off the critical line, then the deviations can be larger, and the primes are distributed less regularly than the hypothesis predicts. In a vivid analogy, the prime number theorem is like knowing that a drunkard's walk will on average make no progress, that the average position is 0. The Riemann hypothesis is like knowing that the drunkard's walk stays within a bounded distance of 0, that the fluctuations are controlled. Without the Riemann hypothesis, the drunkard might wander much further from the average than the theorem allows. With it, the wandering is controlled and predictable. The Riemann hypothesis has been checked computationally for an almost unimaginably large number of zeros of the zeta function. Every zero that has ever been computed lies on the critical line, exactly as the hypothesis predicts. But a finite check, however extensive, is not a proof. And in mathematics, until there is a proof, there is always the possibility, however remote, that the hypothesis is false. If someone were to disprove the Riemann hypothesis, to find a zero off the critical line, or to construct a theoretical argument showing that such zeros must exist, the consequences would be enormous. It would mean that the primes are less regularly distributed than we thought, that there are larger than expected deviations from the logarithmic prediction, that the fine structure of the prime distribution is more irregular than the hypothesis allows. It would overturn a century and a half of mathematical intuition and would require fundamental revisions to large areas of number theory. But most mathematicians believe the Riemann hypothesis is true. The evidence from computation is overwhelming, even if it is not definitive. The connections between the hypothesis and other parts of mathematics are so numerous and so deep that a false Riemann hypothesis would create contradictions in many places. And the hypothesis has a kind of aesthetic rightness to it. The symmetry of the critical line, the elegance of the statement that all non-trivial zeros have real part 1/2, the way it implies that the primes are as regular as they can possibly be. Whether it is true or false, the Riemann hypothesis is one of the great intellectual challenges of our time, a question that sits at the intersection of number theory, complex analysis, and mathematical physics, that has resisted the best efforts of the best mathematicians for more than 160 years, and that, if solved, would be one of the greatest achievements in the history of mathematics. The story of the primes is not finished. But the part we know, the infinitude proved by Euclid, the sieve of Eratosthenes, the conjecture of Gauss, the proof of Hadamard and de la Vallée-Poussin, the 8 pages of Riemann, is already more than enough for a lifetime of wonder. And tonight, having followed the story from its ancient beginning to its modern edge, you have earned the right to let it rest. The primes will keep. The logarithm will keep. The Riemann hypothesis will keep. They will all be there in the morning, exactly as they are now, exactly as they have always been. True and permanent and beautiful. As we come to the end of our journey tonight, the story can begin to settle around you. We have traveled from the tiles of Euclid's geometric proof of primality, through the ancient sieve of Eratosthenes, through the patient counting of a teenage genius in the 1790s, through the connection between primes and logarithms, through Riemann's zeta function and the greatest unsolved problem in mathematics, and all the way to the cryptographic algorithms that protect the digital world today. There is no need to hold any of that tightly now. You can let the details soften into impressions. The image of prime numbers glowing along an infinite number line, rarer and rarer as you go further out, but never ending. The image of a natural logarithm curve, rising slowly and gracefully, mirroring the thinning of the primes with quiet precision. The image of a 15-year-old boy sitting alone with a table of logarithms and a notebook, counting and comparing hour after hour, sensing a pattern he cannot yet fully articulate. Let these images dissolve into the background of your awareness, like the last light fading from a winter sky. The primes are still out there, along the infinite number line, waiting patiently to be found. The largest known prime, as of recent years, has more than 24 million digits. It was found by a distributed computing project that harnesses the processing power of thousands of computers around the world. It is a number so large that printing it would fill a small library. And it is prime, indivisible, irreducible, a pure atom of arithmetic, as fundamental in its way as the quarks inside the proton or the electrons around the nucleus. The universe of numbers is infinite, and the primes are infinite within it, and the natural logarithm of their distribution is as beautiful and as exact as any law in physics. In mathematics, as in the physical world, the deepest patterns are the ones that take the longest to find and that reward the most patient looking. Gauss looked patiently and he found one, and it turned out to be true. Let your breathing slow, let your body settle into wherever it is. The universe will keep unfolding on its own, just as it always has, steady, patient, and kind. Sleep well, good night, still drifting. Let the rain take over from here. Close your eyes and let it wash everything away.